So first, I want to mention that in remaining chapters, we will cover probably chapter 8 to 10. Maybe not entire chapter 10, but 8 to 10. And chapter 8, 9, 10 are all supervised learning with the more nonlinear features. So the linear regression have only identified linear relationships, but chapter 8, the tree-based methods, and chapter 9, support vector machine, and chapter 10, the neural network. And these are all methods to deal with the nonlinearity in relationship between y and other axes. And all methods can be applied for classification and also regression. Support vector machine isn't very strong in regression, but still we have methods for regression. So yeah, when you plan the final project, yeah, at least you can notice that we have more nonlinear supervised learning methods. And you can change the plan later if you haven't included these, but you want to include finally. Yeah, so the tree, just a quick review. So idea is this. So suppose we have several predictors, such as years of experience and the number of hits. Sorry, maybe I should say this is X1 and X2. And then we use the one predictor at a time, and we split the entire group into two, and we see what's the average response is. And we determine the split so that the error is minimized. In regression, maybe we want to minimize the root mean square error. And in classification, maybe we want to minimize error rate or maybe entropy. So in this case, we use the year first, then next we use hit. It's possible that this variable years can be used twice. For example, the 4.5 is the optimal threshold if we are allowed to divide the group into two. But maybe if we are allowed one more, then maybe whether the number of the years is less than 10, maybe the next threshold. For example, the baseball players have higher salary in their prime ages, then maybe if years of experience is more than 20 years, then maybe the salary gets lower. So in such a case, maybe 4.5 and 20 maybe the two thresholds. Probably the year of experience is integer variable, so maybe always the threshold is the integer plus 0.5. But anyway, yeah. So this is the idea of regression trees. So graphically this. So this is the X1 and X2. And we divide the space into the subspace. And in each region that we fit some regression model, usually just constant, but it's possible that we fit, for example, a linear function of X1 and X2. But in such a case, maybe the function is not continuous at boundary. So probably it's not really, it does not really improve the performance. If we fit the linear function of X1 and X2 in each region, then we need 3 degrees of freedom for each region. So that means the 9 degrees of freedom. That is a lot. Maybe it's better to have more splits rather than more complicated function in each region. So the fitted curve looks like this. So this is more digital, so not the very smooth curve. But if the number of splits are larger, then it approximates the true surface reasonably well. And also we discussed more methods to get better prediction performance. And the trees, usually the objective function is used. So usually in regression, we want to minimize the sum of squared residuals, but we penalize the size of tree, because if we allow the many splits, then of course the in-sample performance gets better, but that does not mean the out-of-sample performance is good. And alpha is a hyperparameter which penalize the size of tree, the complexity of the model. Yeah, so the procedure is to make a large tree first, then to minimize this function, then we abandon the sum splits, then we can get the final tree. And classification tree works in the same way. And last time we discussed whether the tree or linear regression, logistic regression work better. And the answer is that it depends on the situation. If the true boundary is like this, then true boundary is linear. So linear regression, logistic regression works better. So this is the classification. So we are comparing logistic regression with trees. But if the truth is like this, the true boundary between two classes are this, then tree methods work better. Yeah, and then last time we discussed the sum extension, bagging, random forest, and boosting. So this is a kind of smoothing methods. So tree gives the very, discrete function. So these methods that do some kind of smoothing. Still, it's not entirely continuous, but the predicted values change more smoothly compared to the original tree method. Okay, so now that we start the exact algorithm. So the bagging is one way to improve trees. So suppose that the training set has n observations, then we repeat the following procedure for b times, capital B times. So at first, the bootstrap n observations with replacement from the training set, then the fit the regression or classification tree. And we so let the f hat of x as the fitted function. Then the bagging, that we take just average of these b trees. So capital B, we have to control this variable, but usually just we can make larger B, then surface is smoother. But if B is too large, it takes too much time. Yeah, and yeah, also we can specify the maximum number of nodes or minimum size of the terminal nodes for yeah, so some hyperparameters we can. So the illustration of bagging. So suppose we have 6 observations. So okay, so think about just that we have one predictor variable and one response variable, and this is a regression problem. And x is here and y is here. And suppose that we have just kind of situation, maybe in which the linear regression works reasonably fine. So x. So yeah, so linear regression works good. And if we do tree, with one split, maybe this becomes this, and the average level is this and this. So this is probably the obtained tree with the one node. Sorry, maybe 2 nodes, I would say. So this is the fitted tree. But the bugging that we use the several trees by bootstrapping. So suppose, okay, so we only have the 3 trees for now. And, oh, yeah. So I think that we should erase this first. So in bugging, we at first the bootstrap observations. So we don't use all 6 observations, and that we consider just the randomized sample to fit the data. So okay. So out of these 6 observations, okay, so we randomize it. So maybe just in case yeah, so random observation. So maybe this one and this one twice, maybe. Then maybe this one, 1, 2, 3, 4, and maybe 5, 6. Okay, so this observation and this observation twice. Then probably the boundary is around here. So fitted tree is here. This is the average of these 3 observations, and the fitted tree is here for average of the observations. So let's say this as maybe A1. And some other cases, okay, so we have another 6 randomized sample. So maybe 1, 2, okay, so 3, and 4, 5, 6, right? Then I think that the left 2 observations are much smaller than the others. So probably the boundary is around here, and average is exactly here, and average is probably around here. So this is another tree, and say this is A2. And the other tree, for example, we have the 2 observations here, maybe 1 observation here, and 1 here, maybe 2 here. Then in this case, probably the boundary is maybe around here. So this is A3, and so this is the mean of these 3 observations. So like this, and the mean of 3 observations. So this is the F1 hat, and this is F2 hat, and this is F3 hat of X. So the bugging, we take the average. So we have the B is equal to 1, 2, 3, and we divide this by 3. So then what happens? So we have the boundary A1, A2, and A3. So boundary A2 is here. Boundary A1 is here. And the boundary A3 is here. So in this case, probably the fitted curve is maybe, I don't know, but maybe here and here and maybe here and here, something like that. So it becomes more a smoother curve. It's not still the entirely smooth, still this is a step function, but it's better than just one step. Yeah. So this is the idea of bugging. So bugging is better in the sense that we can approach to the straight line. Yeah, so why we don't allow maybe more than 2 knots or more than 2 breakpoints at once? Probably that is more complicated because if we want to choose the more than 2 or more splits, then it takes time to choose those, right? Because suppose that we have 6 observations, we have 5 intervals or 6 observations. There, choose just one the point of split is just one out of 5. But if we choose the 3 nodes, then that is 5 choose 3, right? 5 is small number, so it's fine. But this number becomes large, then this becomes extremely large. Suppose we have 100 observations. To make a one split, we have to choose 1 out of 100. But to choose 3 splits at once, that is the 100 choose 3. That is about, I don't know, maybe 1/6 of 1 million. So it's a very large number. So boosting effectively make more detailed step function by exploiting the bootstrap procedure. So this is the idea of bugging. And the other methods are also kind of similar in the sense that we make multiple trees and make an average or some other similar methods. We have questions, just ideas. So if you ask very detailed questions, maybe I cannot answer, but the idea is this. And okay, so next we discussed out-of-back error estimation. So this is basically an alternative for cross-validation or validation approach. But specific for procedure using bootstrap. So in each tree created in bugging, the unused observations are called out-of-back observations. So for example, suppose we have 6 observations, 1, 2, 3, 4, 5, 6 in a training set, and the bootstrapped sample is 5, 1, 3, 2, 3, 5. This is randomly chosen 6 observations with replacement. Then 4 and 6 are not included. So these 4 and 6 are called out-of-back observations. And typically 1/3 of the training set are out-of-back observations. So this does not really depend too much on the number of observations. If we have 100 or 1,000, still it's around 1/3. I'm not exactly sure about the asymptotic results, and certainly if we only have 1 observation, then no out-of-back observation. So the small sample size, this ratio is slightly different, but most of the time 1/3 of training set are out-of-back. So then the idea is, okay, so this is similar situation to maybe 3-fold cross-validation. So we are using 2/3 of observations, and we have another 1/3, the remaining, which are not used for training. So we can do something similar to cross-validation. So that is the idea. And I updated this slide this year, so I have to update the canvas also. But okay, so to be exact, how to use this to estimate error. So we use the sorry. Yeah, so in the out-of-back error estimation, for each given observation, yi, all trees in which yi is not included are used to estimate yi hat. So we bootstrap many times. So suppose we have 6 observations, then maybe the first sample is the 5, 1, 3, 2, 3, 5, and the second sample is maybe the 6, 4, the 3, maybe 2, 1. And maybe third sample is, I don't know, 4, 3, 1, 1, maybe 5, 5 or something. Then suppose we want to evaluate, for example, maybe the 6th observation. Yes, so we want to evaluate this y6. So we want to calculate the y hat 6. Then this set, the first set and the last set, that does not include the 6th observation. So we use this sample, maybe S1 and S3 to calculate the fitted value, the y6 hat. So to be exact, suppose that we have maybe the b is equal to 100, then about 1/3 of these random samples does not include 6th observation. So we use those, the 1/3 of 100 samples to estimate y6 hat. So actually we only use the maybe 66 or 67, maybe 60 to 70 samples to estimate y6 hat. So that is the out of back error estimation. And certainly this is a good measure of test performance because the 6th observation is not used to make a model to fit 6th observation. And any error measure can be used in the out of back error estimation, similar to cross validation. For example, we can use mean square error or root mean square error or mean absolute error for regression, or error rate or deviance for classification. So it's a kind of an alternative to cross validation, but this bagging algorithm already included bootstrap procedure. So we exploit that procedure to do something similar to the cross validation. And here is the comparison of the OOB error and the test error in the validation approach. Just we split the training set and test set. Probably the 2/3 of observations are in training set and 1/3 test set. Then these are the results. We haven't discussed random forest, so we focus on this bagging test error and OOB error. And actually, you can see that the OOB error is smaller. But this is probably by coincidence, and this is just specific for this the data set. And these should be somewhat similar. Of course, it depends on the training data size and the test data size, but it should be somewhat similar. But the interesting thing is the random forest is another tree-based method. In this example, actually, in both methods, the out-of-back estimation has lower error. But as textbook mentioned, this is just by coincidence, and usually it should have kind of similar error size. And the next one is descriptive, not descriptive, but descriptive statistic about the tree-based methods. And it explains which variables are more important. So this explains how much each variable reduce the error size. And actually the variable with largest contribution is the baseline. So it's fixed at 100. And we see how much other variables reduce the mean square error or some error measure. And yeah, so more important predictors are at the bottom. Yeah, it doesn't explain it clearly in the textbook, but I think that probably this is the leave one out contribution. So compared to the full model, if we drop the THAL variable, then the error size so if we exclude THAL, the error size increased most. Yeah, and the next one is the random forests. I think that we briefly discussed this. So random forests are the same as bugging, except for the number of predictors allowed for each tree. So in bugging, if we have 10 predictors, we can use all predictors to make each tree. In random forests, each tree is allowed to use randomly selected M predictors out of P predictors. Often M is just 1/3 of P or square root of P. So we can specify this M. So it's a kind of hyperparameter. And if M is equal to P, random forests are the same as bugging. So the idea behind random forests is to diversify the tree generated. So if we do some estimation procedure, if we have more variety, then the overall result is better. Maybe that is politically nice, right? So diversity helps the overall performance of the society. Yeah. And here is just the prediction performance between the bugging and random forests with M is equal to P over 2 and M is equal to square root of P. It doesn't shows what example is used, but you can see that it really depends. The performance really depends. But if we carefully choose M, then that is better than bugging. So green one is better than bugging. But actually, the blue one performs even worse than bugging. So not always random forests are better than bugging, but at least one more parameter. So usually, if we tune that parameter well, then the test performance gets better. Yeah, so basically the bugging and random forests are the same. Random forests restrict the number of predictors used in each step. And the boosting is a method of slowly fitting a statistical model. So that is, the fitted values are changed by a small amount at a time, but the model is fitted many times to obtain final predicted values. So boosting is a general approach that can be applied to many statistical learning methods for regression and classification. So it's not only for trees, but also for usual regression model. So algorithm is here. So I think that it's good to have y bar is equal to 0 first. So we adjust the constant. Then the set f hat x is equal to 0 first for all x. And we define the Ri, so residual sub I is equal to yi for the first time. Then we repeat this procedure. So at first, the fit a tree with the D splits. So D depends on your choice. D usually is 1 or 2 to the training data. So D is a kind of this similar parameter as M in random forests. So for each tree, we only use the D splits. So not the D variables, but the D splits. And update our estimate f hat by adding a fraction of a new tree. So f hat, new f hat is old f hat plus lambda times the b f hat b. So f hat b is the usual, the regression fitted value. So regression fitted value. And lambda is a kind of small step. We can assume that lambda is 0.01 or something. So we slowly change this f hat. Then we update this residual. So this is the new one, and this is old one. So new residual is old residual minus lambda times f hat b. So it slightly changes. Then we repeat this. So this procedure is sequential. We cannot define f hat 2 if we didn't fit the f hat 1. So bugging is just average. So maybe b is equal to 100. Maybe 100 different people fit the model, and you can share the job. But here, this is the sequential, so you cannot divide the job. Yes, but you know, the updating residual is a good strategy, because if always we fit y on x, you always get similar results. But if you fit y on x, then okay, so suppose the result is the a plus bx, y is equal to a plus bx, then we think about residual. So residual is a good information if, for example, we want to use the another predictor x2 or x3. Because basically we have already considered what x can explain y. So we are thinking about the remaining part. Then we fit, for example, r on x2 or r on x3. So that is sometimes much more effective than fitting the same regression model again and again. Yeah, I think that do you know that Zillow is a real estate website. And if you know, and Zillow has the estimate for the price of your house. So every house in the United States, and they have some model, but the model isn't really correct always. So in the past, usually the model is good, for typical houses. But if houses are very cheap or very expensive or very large or very small, the fit is not good. Then they did some Kaggle competition to explain the residual of the house value. That is good because Zero already have several basic information such as the size of the house or how old the houses are, and they just want to exclude those factors, and they have a competition to explain residual. So explaining residual is one good strategy, and this boosting adapts that strategy. It's so finally f hat is so we can write f hat as the summation of this, but each part is the f hat b can be obtained only after f hat b minus 1 is obtained. And there are several hyperparameters in boosting. So one is the number of trees. And larger B may overfit the model. It's a kind of strange. So if we do this again and again, intuitively it approaches to the truth. But if we do too much, then it overfits. It's a kind of strange, but that can happen sometimes. And lambda is a kind of step size, the shrinkage parameter lambda. So use a small positive number such as 0.01 or 0.001. And this isn't very essential parameter. So if lambda is too large, that's a problem because the step size is too large. Lambda is too small, then the improvement is very modest in each step. So we need more steps. So the step size is not very crucial, but if lambda is small, then we should have a large B. And the number of splits in each tree, this is another hyperparameter, but often it's set to be 1. So this, if we make this 2 or 3, the computation is heavier, but the performance does not improve much. Last year I explained the image of boosting with the I think last time we mentioned it. So basically, if we have So this kind of observations, then, okay, so just for simplicity, this is 0. Then the fitted value is this by usual tree. Maybe I put 0. But boosting only reflects a small portion. So just we assume that this fitted curve makes this level slightly higher and this level slightly lower, and this is the this is f hat b, and this is the lambda times f hat b. And we again take the residual. Then we use this residual to fit the next f hat b, f hat b plus 1 maybe. Then we repeat, and this variable that changes for different iteration. So in the next iteration, maybe we use x3. In the next iteration, we use x7, something. Then gradually we fit the surface. So y on, for example, x1 to x10. And so the reason that d is equal to 1, not the reason, but we often make the d is equal to 1, and it corresponds to a kind of linear model. So, you know, the linear model y is equal to beta naught plus beta 1 x1 up to beta pxp plus epsilon. And in this case, we don't have any interaction between x1 to xp. So in this case, basically in boosting, we only need d is equal to 1, because we don't have to describe the interaction. And basically this part can be obtained if we repeat the procedure many times. So we can pretty flexible relationship. We can model the relationship between y and x1 pretty flexibly with this boosting procedure. So if we have interactions, then we have to make multiple splits with multiple variables. So we need the d is equal to 2 or 3. So basically d is equal to 1 corresponds to the linear model, and d is equal to 2 corresponds to the linear model with interaction terms such as x1, x3. And d is equal to 3 corresponds to three-way interaction such as x1, x2, x4, something like that. So this is the boosting. And this is one example of boosting performance. So this is, the green one is random forest, and the orange and blue are boosting with the d is equal to 1 and 2. And actually d is equal to 1 looks sufficient. D is equal to 2, maybe this test performance gets worse. So d is equal to is more complicated model. So training error should be small, but it can overfit the situation. So test performance can be worse. And here, this is b, number of trees, this is b, and lambda is set to 0.01. And it sounds that the large b is just fine. So we don't really overfit the situation. So if this becomes larger, then we have to stop at some point, but it sounds just large b is fine. And I think that's consistent with my experience. So usually it takes too much time, so we have to stop at some point. But, that's the case. Yeah. Do you have any questions? Okay, so now we want to decide the presentation date. So I will share the screen from my computer. So share screen. Okay, so 19th and 21st and May 1st. May 1st, I think the time is slightly different. But yeah. But
6:30 to 8:45.
Oh, sorry, 6 to 8:40, 8:30, sorry.
6:30 to 8:45.
Okay, 6:30 to 8:45. Yeah. Yeah. So I got the request from one student, the target, who cannot attend, and he cannot make presentation on April 19th with convincing reasons. And May 1st isn't preferred because of other final schedule, but that is his request. But do you have any other preference? You can pick date. Especially, I think not all students are here. So
yeah, Boyke can do the 24th of the 1st. I'm coming home from a long weekend with my wife for a 34th wedding anniversary. So I'd rather not do a presentation on the 19th. So 24th or 1st, whichever one you want to put me in.
21st or 19th. Okay, so
24th or 1st.
24 or 19th.
Get rid of the 19th, 24th or 1st.
First, sorry.
Thank you. I do not have a problem with either date.
Okay. Oh, are there any people who want to make the presentation on the first day? Oh, and I will comment on your presentation plan based on the presentation date. So that means, May 1st is, the 12 days after 19th, but that does not mean you have the 12 more days to prepare. Maybe slightly more than more time to prepare, but yeah, actually to tell the truth, actually if your presentation dates are higher or are earlier, then more students meet the deadline.
If you need,
because the final week is the final exam.
I can do the 19th if I absolutely have to, but I'd prefer not to.
Do you have? Are there any students, especially if you have already made a presentation in the past class, the previous course of mine, then maybe we can.
Yeah, I do 19, Professor.
Oh, you did? Yeah, okay. Big story.
Thank you.
Yeah, I can do the 19th as well.
Oh, okay, great. Hunter?
I can do it too.
Sorry.
On the 19th. Oh, I can do it. I can do it on the 19th.
Oh, well. Okay. First day? Okay.
No, Nathan, sorry.
Sorry?
Oh, it's Nathan.
Oh, Nathan, sorry.
I can also do it on the 19th.
Oh, okay, good. Zoe? Okay, then others, maybe. So Bill, so 24 is the best date for Bill or first?
I don't care. If you absolutely had to, I could do the 19th, but I'd prefer not to.
Yeah, 19th we have already 4 people, so I think it's fine. Yeah.
All right.
And other people, how about?
Yeah, I don't have any other classes, so I don't have to worry about finals.
But I prefer doing it on the 24th, if it's possible.
Sorry, James?
Yes.
Okay, yeah. 21st?
So, thank you.
I'd also prefer to do the 24th if possible.
So Erica? You
Yeah,
said- Sorry, yeah, I have trouble. See.
thank you.
Okay, so and the Thomas, do you have any preference?
I don't really have a preference, so you can just put me down on the first.
Okay, decide later.
Or you can do me last. It doesn't really matter.
And how about Ryan? Rayan, sorry, Rayan.
I would prefer to do the 19th.
Oh,
but-
okay.
I don't know if I can do it that late.
Okay, so sorry, maybe we have to move one person to later date. Sorry. Any volunteer to move to another date? I think 5 is a little too many. So, last day we can have 5, even 6 or 7, but I think the 4, 4, 5 is a good number. So, sorry. So, Victoria, Hunter, Nathan, can one of you can move to
I can
either
go to
21st or 9th?
Yeah, I can go to the 24th.
Okay, great.
Yeah.
Okay. Oh, sorry. And any other people here today? Thomas, James, Erika, Ryan, Zoe, Bill. I think these are all. Okay, then I put other students maybe calling here. And yeah. So I'll hit Michael. Okay. Luke. Oh, Luke. I'm not sure. Okay, I think that should be fine. Just in case, I want to quickly check the email to see anyone request something in the last minute. Yeah, I think I didn't have any requests, so yeah. Okay, I think that's fine. Okay, so I will send this. I will upload this to Canvas. So yeah, and the presentation is 30 minutes, but I think it's maybe we can say up to 15 minutes, maybe 10 to 15 minutes, 10 to 14 minutes. Yeah. Okay, so do you have any other questions on the final presentation so far?
I have a couple,
And
but I'm going
attend all
to.
presentations. Okay, so just respect your classmates. So I'm paid, so if you skip, that's fine. That's students are not paid. So if you even make a presentation on the first day, just attend other presentations, and I will ask you to comment on it. Yeah. Okay, great. So now that we go to the lab session. And, yeah, and we will do exercise. So I just want to quickly go over this. And first, the classification trees. So first we do trees, then after that random forests and bugging, then after that boosting. And the classification trees, I think the implementation is pretty simple. So we need just the tree library. And this is for data. So this is for car seats data. This is, I think, the child seats. Imagine that child seats are sold in Target or Walmart. And we have 400 different observations, so 400 different child seats. And we have the sales amount, and this is the competitor's price and income level of the sorry. So this is the sales of a specific car seats in 400 different locations, and this is the sales amount. So this is the competitor's price, and this is the income level of that store, and the advertising spending on of the store, and the population size of the the town where the store is located, and the price of the product, and the shelf location. It matters for sales. Maybe average age of the town and average educational level of the town, and whether town is urban or not, and whether the location is in US or not. And so this is sample data. So first 6 observations. And we do classification tree first. So actually this sales is the response variable, but this is a kind of artificial example. And we explain whether the sales is more than 8 or less than 8. I don't know the unit, maybe $1,000. So we define this factor variable, then we do the classification tree. So this is the data for the predictor variables for this data set. So just we exclude the first column, that is sales. And this just erase the high variable, which has already is included in the dataset B. So to avoid confusion, so we erase high. So we created high, and we make this variable included in D. So we just eliminate original one so that we don't have any duplications of objects. Then, okay, so 3 function can fit the data. So this is exactly the same as the LM format. So we have LM y on x, but we have just the same thing. Dot means that all variables, so all other variables done high. So this is exactly it exactly works in the same way as LM. And this is the result. Yeah. So I think there are some, preset parameters, such as maybe the number of maximum nodes, or maybe the minimum number of observations in each node or something. So it stops at some point. And this is the the result of the tree. So it has actually 27 terminal nodes, and the classification error is 9%. And the residual mean deviance, this is a kind of likelihood function. So this is 0.4575. And this is the graph. So at first, it splits the variable, it splits the data into the shelf location, bad, medium, or probably good. So we separate these two. So the shelf location is the most important factor. I mean, the first factor to consider. Then after that, the price level matters. Actually, for each node, the price level is the second factor to consider. Then the income level, and so on. So we have some then it's so clouded, so we cannot really see. But after we split by income level, we use the competitor's price, or I don't know which this one, but yes. And at terminal node, we can see whether there are more no's or more yes. And actually, this is yes. So it's kind of strange, but this means that this split does not make any sense. Yeah. So in this way, then we can get 3. And we can apply the predict function on trees. And this, if we set the type class, then we can get the predicted category. Then this is the true category, the actual, and this is predicted, and you can get the contingency table. And you can see actually the 36 out of 400 are misclassified. So error rate is 9%. We have seen before, seen above, but the 9% classification error. But this is in sample. So we use just 400 observations and make a tree. And we use this tree to see how many of 400 observations are classified correctly. So to make a fair judgment, that we need a test error. So we split the training error and the test error. Okay. Always we have to randomize. So 200 out of 400. In this case, I set the 200 observations for training set and 200 observations for the test set. And we define this as DTRN and DTST. And we do training with training set. We fit the data with training set, and that we predict the training set. So this is in sample error. So this is this. So this is actually 20 out of 200 classified incorrectly. So error rate is 0.1. So this is pretty reasonable because previously we said C 9%. So it's similar to 9%. And also our sample size is just a half of 400 observations. So model is slightly less accurate. So it's pretty reasonable result we get. And now, we use the training set to do cross-validation to see what's the best model. And this is the size, this is the tree size, so number of nodes in tree. And this is the cross-validated error, even though it says deviance. And K is the hyperparameter, so it's similar to alpha. And I think this is probably something like the log of alpha. So it's transformed version of hyperparameter. So we are minimizing, the sum function error rate or deviance plus alpha times tree size. So we minimize this function and remember that the alpha is a hyperparameter. And here, K is a kind of similar to alpha, but probably it takes the logarithm of alpha so that it starts up from negative infinity and ends at 20. So K and size corresponds each other. So this corresponds to this, and this corresponds to this, and so on. So K gets larger, the tree gets smaller. And the tree size is discrete, so we only have the maybe 18 possible Ks corresponding to each size. And the measure to see is the deviance. We want to minimize this. So here or here are the best. So that means the 5 or 6. The tree with 5 nodes or 6 nodes are the best for this example. Or the hyperparameter corresponding value is either 2.5 or 3. And actually the misclassification is used. So this is the function to minimize. And this is the graph. This is the size against the cross-validated error. Yeah. So here it says deviance, but probably this is because of some other functionality of this the tree package. So it says deviance, but I believe that this is cross-validated error. Yeah. And this is the similar graph, just it shows the same graph differently. So this is the parameter size and the deviance size. So actually, you can see that this is, for example, 68 maybe, and this is 15. So this corresponds to 68. So it is. So basically, we flipped. So the left-hand side and right-hand side are flipped, but and also the scale are a little different. But basically, we have the same graph. These are the at minimum, and these are at the minimum. So it's the same thing. So the tree size is either 5 or 6. Oh, sorry, 5 or 6. I thought 5 or 6. Yes, yeah. And the k, the size of k is, I don't know what's the exact value, but here or here. So we can prune the tree with this 5 nodes. Then this is basically the best results. So based on these results, okay, so this explains, how many observations are classified correctly. I think that is the, yeah, so the indicator variable, so the response variable is the whether cells were larger than 8-1, and this is the proportion of that. So if we split the entire data set by what's this? I'm not sure about this split, but with this split, then 58% have the cells more than 8 if the value is less than the threshold, and more than threshold, the 42% of observations are cells less than 8. And next, price, and the other way around. Yeah, sorry. Let me explain again. So the sales is more than 8. This is the predictor response variable. So this is y. So indicator variable of this. And this is the overall proportion. So overall proportion of y is equal to 1. And this is overall proportion of y is equal to 0. Then the first split, the price is either the more than 92.5 or less than 92.5. And if price is less than this, then the 87.5% the sales is more than 8. And price is more than this, actually only the 33% of the stores have sales more than 8. And we split further in each node. And actually, if price is lower, then that's fine. And price is higher, then other factor comes in. So that is the final tree. Yes, so we can get by specifying the number of terminal nodes, the 5 nodes. And we can also specify in another way. So for example, we can specify the parameter k is equal to 3. You can also change the method to prune the tree. So we minimize the classification rate or we minimize the deviance. So it's a little bit hard to imagine that once you make a large tree, that we prune the tree so that the objective function is minimized. So that means originally we have, suppose, the 18 splits, but we don't know which split will be eliminated. Yeah. So then this, yeah, and yeah, then after that, we want to see the prediction performance on the test set. So we use the predict function to make a prediction for the test set, and the type class returns the classification, so which class each observation belongs to. Then we make a table of the actual and the predicted. Then this is the table. So sample size for test set is 200. And we have actually the 20 and plus 34 incorrect. So that means the error rate is 54 divided by 200. So that is 0.27. So this is much larger, actually. This is much larger than training set. And tree method often the overfits easily, pretty easily. So, you know, originally we fit a large tree, this, and error rate is 9%, but, or maybe only half of the observations, still 10%, but if we check the test error, that is 27%. Yeah, do you have any questions? And this is a huge typo. So this is next topic is regression trees. We have already done classification trees. So we use the same package, the tree package. And we now the predict scales as a continuous variable, quantitative variable. And this is you are familiar with this, and this is the pairwise scatter. The relationship is vague. Maybe the advertisement amount matters. Maybe too many observations, so we cannot really see the specific pattern. Maybe this is clear. The price and advertisement there matters for sales. And the other variable, maybe age also matters because this is for child seats. And the categorical variable, it's really hard to see because yeah, many observations are at almost the same race. Maybe shelf location matters, you can see. Not clear here. Education, not really clear. So far we can see advertisement, price, and age matter for the sales. We can set the order of the factor variable so that we can do optimal split. I'm not exactly sure when the usual categorical variable is used for in tree. Maybe one and the others, or they try all combinations, probably no. But if we set the order of categories, it's clear that either the separation is here or here. Yeah. And this is correlation plot, so price, shelf location, age are important. Maybe US or not, income, advertising. So these are almost also important. A correlation plot can be made with these numbers. And training and test set, we create it again, and we do regression tree here. So regression tree, so these are average values, so not yes or no. So it's different from classification tree. And so we do the cross validation, and we see which is the best, and you can see which maybe 760 is the best, maybe so the tree size of 12 is the best, maybe. So K value of 20.05, maybe. Then we have, sorry, the 9 is the best. Sorry. 1, 2, 3, 4. Yeah. You know what happens here. So I use the RStudio. RStudio compile the file each time, and the cross validation is different each time. So probably last time I did the 9 was the best, but this time actually 12 is the best. So we have some discrepancy, so it's kind of confusing. But okay, so but it's reasonable to use 9 to 12 maybe. Then we use 9, then we can do pruning. So we make the best 3, kind of. Then we calculate training error. So training error is here. So we use the prediction. And this is the plot between actual and predicted. So this is 3. So 3 has, okay, so 9 nodes. 9, sorry, the 9 nodes. Yes, 9 nodes. So we only have 9 levels here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, that's 9 levels. So predicted values, only the 9 possible values. So each node we calculated these numbers. Right? So we have, so this is the entire tree, but we prune this into the tree with 9 nodes. So we only have 9 possible values. But still, we have pretty high correlation between actual and predicted. So it sounds reasonable. And the error size, this is the mean square error for training. So this is 2.56. We do the same thing for the test set to calculate test error. What's the test error? So this is test. It looks reasonable, maybe slightly lower correlation. Maybe we should flip the predictor and the actual. Anyway, but actually the MSE gets much larger. MSE gets much larger. So 5.18. So it's almost twice as large. Even when we take square root, maybe 1.4 times larger. So it overfit the situation. I wouldn't say overfit, but the 2.56 is underestimates the test error. Still, it's the best model, but the training error is much smaller than test error. Yeah. Yeah, so 8.1 we finished, and okay, so and the okay, we compare the 3 results with usual linear regression. So this is the kind of the baseline model. And if we use the usual linear regression, actually these variables are all significant. And I use stepwise procedure. So I dropped unnecessary variables. Then actually the mean square error is 1.11, 1.12 for what the training set. And sorry, this is test. For test set, actually, this is coincidence, but the actually test error is slightly smaller than, even smaller than 1.089. So actually, this is much smaller than 5.18. So the regression tree that does not work much, does not work well compared to the linear regression. So later we will see the bugging and random forests results. So these models perform much better. Okay, so we stop here, and next time we do the remaining part and also exercise.